All right, so standard announcements. Money's point due this weekend. Mini project 2, which is an optional mini project. So remember you drop, I think, how many projects we dropped, but we dropped several mini projects. I don't want to misquote myself, and so the idea is that you only have to do like 2 or 3 for the semester if you liked topics from Unit 2. So topics related to evolution strategies, genetic programming, or immunocomputing, then it's an opportunity to pick a topic from that unit and then build a short demonstration of some principle from that topic, from that area. So similar scope to mini project 1, just without the questions being kind of given to you. So 1 to 2 pages to demonstrate some principle from that. It doesn't have to be from everything in that unit, just one thing that you would like an opportunity to implement and experiment with yourself. So it's just an opportunity. Concept check 3A and 3B. Extended these a little bit so that 3A is due this Sunday and 3B is due the Sunday at the end of spring break. So those 2 are spread out a little bit more. I do want to comment a little bit the moneyest points. Really appreciate the time a lot of you put into the moneyest points. I do want to emphasize though that I'm not looking for you to spend a lot of time in them. So it's totally fine to just take 5 minutes to say do a mental inventory of what were the things that we talked about this week. If there are things at the end of the week that I say that we're going to talk about the next week, you can exclude those because they're probably going to be muddy just because we haven't talked about them. We haven't really gotten into them. We just kind of get a brief intro to them. But take an inventory of all the topics that we kind of completed that week and just sort them, or at least find the thing that's clearest, the thing that's muddiest. And it could just be a 2 or 3 word description and then put those in your answers. You'd like to expand on that because you'd like to see if I could comment more on something just for you in the comments to the moneyest point, that's great. But that is something that it's your opportunity to do, but it's not the sort of the expectation. So it's totally okay if you're crunched for time, you just want to take 5 minutes on this. You don't have to spend an hour to sort of craft a complex response to each question. So just putting that out there just to kind of level set our expectations. All right, any questions? The mini project 1, from what I understand, has been graded by the grader. I just haven't released the grades yet because I want to go through and just do a spot check of some of the grades and see how things look before I release that. So I should have that released in the next couple of days. All right, so we left off last time where it's a new unit. We're focusing on multi-objective approaches. Multi-objective evolutionary algorithms is ultimately where we're going. But we start out a little bit more just thinking about multi-objective more generally through looking at mathematical decision theory, specifically game theory, and multi-objective optimization. 2 things that fall under decision theory that both have this topic or this concept of the Pareto-efficient set that is kind of links those things together, which we'll talk about here. So this is a normative framework. It's not descriptive. This is not behavioral economics. So these are, if you had a bunch of rational decision makers, what would you imagine they do, or what should they do? What describes kind of outcomes from these rational decision makers working, against each other or with each other and Gesundheit. And not only could this apply to sort of setting up benchmarks for thinking about social outcomes in real life, but it also can be viewed to describe things like when you start bolting together neural networks, one that is adversarial to another. So one that generates challenges, the other one generates responses, and those kind of go back and forth, so-called generative adversarial networks. Those networks, now you've got a gradient descent algorithm running on one agent and another gradient descent algorithm running on another as they're being trained together. And the combination of those 2 together, as we'll see, fits the frameworks of these game theory. And so solvers built to solve game theoretic equilibria are now being used to better train these combinations of agents when you put them together. So especially as we start moving more, now things are a little bit different now that we're in the kind of post-training world, now that we're in large language models that are sort of already frozen. But back when generative adversarial models our networks were more popular, then we found that that this was a framework people were starting to use to solve these things. So I'll mention that a little bit more as we go on. But so the basics there we started out last time was a basic in-game theory is that we have a number of players. So you can think of these as agents, you can think of these as actors, that each one have control of one decision variable out of many. So player 1 controls x1, player 2 controls x2, and so on. x1 could actually be a vector. So x1 could be multiple variables combined together, but the point is that all of the variables in the sort of decision space, a subset of them are controlled by each player. So every player's payoff, or in this class, payoff and utility mean the same thing. And in every player's utility or payoff depends upon not only their actions, but the actions of those around them as well. They might have different payoff functions. U1 is different than U2, but all of their payoff functions potentially are affected by the actions of themselves and others around them. So that's a general outline of a game. And then in a game, we have different equilibrium concepts. And so the Nash equilibrium is a very common one that's actually very useful in engineering for reasons that I'll talk about here in a second. But a Nash equilibrium is a set of strategies. So it's a set of things that those N players will play such that, and I'll use this shorthand sometimes, where instead of writing this entire long sequence here, vector, then if I'm just focusing on one member of that vector, one element like xi, rather than writing this the whole way, I might just say we're focusing on I right now, and so we've got I, and then everything else that is not I just bundled up into there. This is just a notational thing. And so a Nash is a strategy X star such that for every player, this will be the case. That if that one player I considers changing their position, trying a different strategy xi, and only they change, then the utility or the payoff that they get from that change, from that unilateral change, is going to be no better than where they were at the Nash. So if there is a position that a single player could move to with everyone else staying the same that gives them a better payoff, then that will be the Nash. And the thing we were at, it won't be in the Nash. So there can be multiple Nash equilibria in a game. There could be just one. And there could be no what we call pure equilibria, and there'll be what's called mixed equilibria, where some players will be playing some Nash, and other players will be playing some other Nash, and the equilibria will be the fraction of those playing one versus another. So that's it goes out kind of outside the scope of this class. It's called a mixed Nash. But so the point is, don't always count on there being just one. There could be multiple. There could even be zero, and then there could be these weird hybrid Nashes as well. But are there any questions here about this definition of a Nash? This idea that everybody might be able to do better, but it would require collective action. Without collective action, this is the best you can do. And this is what has made this for parallel numerical algorithms, for distributed algorithms, very useful, because this is kind of like the solution with anarchy, with no communication, with no coordination. If you just have a network of agents that are running around that are making changes that affect the other agents, but they don't necessarily have a way to communicate with them, then you would expect those networks to sometimes settle into Nash. And so if you can understand what the Nash is, then you can understand over time what is going to happen with that multi-agent system. So there's applications here in multi-agent reinforcement learning. So you got a robot that's learning about its environment, but as it moves through environment, it depletes resources that affect the payoff for other robots and so on. That's one example. You've got computers on a network, and this computer is deciding there's a pool of tasks, and they're signing up to take those tasks. And as they take tasks out of that pool, it affects the payoff of other computers on that network. So the strategies that you build that are running in parallel they're locally greedy, so they can be run by kind of a local gradient follower. And if you try to say, well, what's going to happen to the network if I put a bunch of these things together? And that solution is often described by a Nash. And so if we have a way to solve for Nash equilibria in a wide variety of systems, we have a way to describe some of these decentralized systems that we build in engineering contexts. Okay, so so let's get some. So, I'll pause there. Any questions on any of that? Okay, so a simple case. This is for a so-called discrete game. So discrete games and continuous games. Discrete games are when every player strategy comes from a countable set or a finite set. So in this case, I've got two players, and this is called the Stag Hunt game. This looks a little bit like a prisoner's dilemma, if you've heard about that before. If you haven't, that's fine. The prisoner's dilemma is sort of an overused example in kind of introductory game theory. It turns out that the prisoner's dilemma is actually not very helpful at describing what goes on in nature or in social systems. It is just put out there to pose an interesting problem, but it's much more of kind of a puzzle than it is sort of a helpful model. The Stag Hunt is sort of you can almost think of it as a modification of the prisoner's dilemma to make the prisoner's dilemma actually more realistic or useful. So in a Stag Hunt, we have two players, and you can think of them as hunters, and one of them, and they can each decide to either cooperate and play stag, which means that, so in the hunting narrative, there is a giant ungulate, a moose out there, a deer out there, a giant animal that one hunter cannot kill and or cannot find and secure by themselves. And so you need two hunters in order to secure the stag. And so if both hunters choose to go in on that, play stag, then they're both going to win that stag, and they'll both be able to share a lot of returns from that. So if they both play stag, then they're both going to get, and this the way this payoff matrix is written, is these triangles. So this is the case where they both play stag, and the upper triangle is the payoff that goes to this player, and the lower triangle is the payoff that goes to this player. And so in this case, if they both play stag, then they both get 10 units of payoff. So 10 calories, $10, however you like to say. The key here is that this will be the greatest payoff that they can get, as if they work together. Now, it might be that one hunter decides instead that they don't want to go alone. They don't want to go in on the stag. They want to go alone and go for a hare, like a rabbit-like animal. This, little animal. There's a bunch more of them, and you can secure it on your own. And so, if this hunter decides to play hare and this hunter decides to play stag, then because there's only one hunter looking for hare, then there's a good chance that the hunter playing hare will find the hare all on its own and will get a pretty high reward for playing that hare, close to the reward that they get maybe for playing stag, but still less than that. But the one who went for stag alone has a very low chance of getting that stag on their own, and so their expected payoff ends up being very low. So if it helps, you can think of these as expected. So these are sort of like probability weighted. So, if you think about every once in a while they get the stag on their own, but it's very, very rare. Most of the time they don't, then maybe the average payoff is 1. Now, if instead they both went hare, so they both decided to go alone, they're both guaranteed to get an animal, but it might take a little bit longer. It might be harder to find. So they both get the reward, the same reward for going hare, but it's a little less than the reward you get if the other one went stag. And this is the symmetric case here. So these two cases are just whoever went the other way. So if you're familiar with the prisoner's dilemma, it's very similar to that, but in the prisoner's dilemma, this is enriched so that if you happen to be the one who goes alone and the other one decides to do the cooperative thing, then it's actually best for you in that particular case. So in the Stag Hunt, this is the ordering. A is greater than B is greater than C is greater than D. In a prisoner's dilemma, then B and A swap. And so it just turns out that there's very few social interactions in nature or in human society that are that kind of evil as the prisoner's dilemma, where it's so enriched to screw over your neighbor. And so most of the time, the things look a little bit more like this. All right, so this is the Stag Hunt, and we want to look at the equilibria of this game. Before we get into that, any questions about the setup of the Stag Hunt? Okay, so the Stag Hunt is interesting because it has two Nash equilibria, unlike the prisoner's dilemma, which just has one. And those two Nash equilibria are the ones that are highlighted. They're this upper one and this lower one. So if you live in this world where both play stag, if the other one keeps playing stag and you decide to play hare, your benefit will decline. You'll go from a 10 to an 8. So that's not good. So if you're both playing stag, you should both continue to play stag. Now, if instead you're both playing hare and you're both getting a 5, there's also no benefit for you to change. If you start to play stag when you're playing hare, then suddenly the one who's playing hare will get an 8 and you'll get a 1, so it'll go down. So in both of these cases, if you're in this world or this world, there's no benefit to change, if only you are the one to change it. So there's two Nash equilibria. So then the interesting question is looking at these two Nash equilibria. So the upper corner here, this equilibria we refer to as payoff dominant, and it looks like, let me change my eraser settings here, sorry about that. Surprised it hasn't happened already. So it's payoff dominant, which means that between these two equilibria, you're going to get the better payoff by going with the upper one, if you can live in that world. In fact, it's what we refer to as socially efficient. So this is the first introduction. I'm going to formally define Pareto when we get into multi-objective, pure multi-objective here in a second. But in short, the beauty of this solution here is that there's no way for the society or the two individuals to do any better. So there is no movement that would benefit both members. If you were in this equilibrium, if you both managed to move up here, that would be better for both of you. So we say this one is not socially efficient because there is an improvement you could make that will improve the outcome for both players. So this is the payoff dominant, socially efficient, or so-called Pareto-efficient solution or equilibrium for this particular case. So that would be great. This is where you want to be. Everybody wants to be playing stag with another player playing stag. In the prisoner's dilemma, again, if you've heard of that one, it would be nice if you cooperate with another cooperator, but what you really want is to defect against a cooperator. You want to screw someone over. Here, you really want to be paired up with another cooperator. It's better for both of you. If you go the other way here, it actually screws you out of a little bit of benefit too. So you really want to be here. But it turns out that in real Stag Hunt games, and this matches to a bunch of public good games, that you don't see everybody cooperating. And so instead you see people down here, and we have to say, well, what's so special about this equilibrium? Why would anyone choose this equilibrium if it is actually better to be in this equilibrium? And this equilibrium is what we call risk dominant. Because there is no way to guarantee that the other player is going to play stag, it's just safer to play hare. The variance in outcomes is lower if you're playing hare. So if I play hare, so I'm the blue one, the one on the right side here, I'm either going to get a 5 or an 8. But if I instead play stag, I'll either get a 10 or a 1. So in this column, I have a greater risk, a greater variance in my outcome. It's either a 1 or a 10, whereas here it's pretty buffered. So if I don't know whether the other player is going to play stag or hare, if there's no way that I can communicate with them, no way I can guarantee, I don't think they're going to screw me over. I just don't have any assurances about what they're playing. Then in that case, it's just safer for me to play the so-called risk-dominant equilibria here. Minimizes the variance in the outcome. It's just safer. Question?
I was going to say, it seems that if you're following like specific strategies, like a min-max, means that you should always choose there.
That's a min-max is a worst case scenario, is a risk dominant. Absolutely, that's exactly what we're saying. So if I really want to say, and that's a beautiful way to put it, if I want to maximize my minimum, so if I want to maximize the worst case, if I want to make it the least bad solution, I play hare. Unless there's some way I can get assurances that the other one is going to play stag. So this is what's called in game theory a coordination game, because the two equilibria are equilibria where the strategies match among all players. So we can describe the equilibria. There's no equilibria where there's a mismatch. There's no symmetry breaking you have to break where it's to sort of say, it's like a stoplight, there's symmetry breaking there. You see a green, you see a red. I can choose to go through the intersection, or I can choose to stop at the intersection. That's a hawk-dove game. That's a game that is an anti-coordination game. So, and that the symmetry is broken by the light itself. And so if you see a green, you drive through the intersection. You see a red, you don't. If you deviate from that strategy, it's going to be bad for both of you. And that's what breaks the symmetry. And then you get someone who cooperates, and that's the one who stops, and someone who doesn't, that's the one who goes. But here, this is a coordination game. The equilibria are where the strategies match. And it's specifically a type of coordination game known as an assurance game. And this goes back to this worst case scenario, is that the key problem is assuring that the other player will cooperate. It's not a challenge of competition or exploitation. It's a challenge of coordination. So, and this also, when you're an engineer, this should resonate. Because a lot of times if you say, if I've got a multi-agent system, or I've got a bunch of nodes on a network, then the real question is not, is it good for them to all agree on a next action? So how many people, this is going to show my age, but how many people have heard of the Byzantine generals problem? So if you ever take a distributed computing course, maybe, I have no idea if they still teach this stuff, but if you took a distributed computing course, you learn about these famous philosophical models that are used to think about problems like like a bunch of computers, they're on a file sharing network. They all have to agree on who is the master of that file sharing network. There's one computer that keeps track of all the other computers to say that, to say which one sort of, if you want access to certain files, you need to go to certain computers. And there's one kind of authority for that. So the first thing these things do when you turn them all on is elect a leader. They all have to agree on a leader. And so you don't care what leader they agree on, but they all have to agree. So how do you guarantee agreement? And you do potentially have adversaries, so you have people trying to break that up, but then you just have environmental noise. People turn off the computer that was the leader, and now a new leader has to be elected. So there's a coordination issue. And a lot of what we do when we build algorithms on networks is solve the coordination issue. We don't worry, now maybe nowadays, now that we have whatever Moltbook and all these, now that we have agents running around that supposedly have their own mimics of agendas, maybe we do have to start worrying about prisoner's dilemmas and so on. But generally speaking, when we build technology and we put them on networks together, we don't worry about them trying to screw each other over. We worry about them coordinating. So that's why this assurance game can become a more useful framework to kind of think about. And so key things I'm trying to have you take away from here is that you can have multiple Nash, not just one Nash, and this idea of Pareto efficiency, which is an idea we're going to develop more when we get to formal multi-objective here in about 2 slides. That is something which is a separate concept. So sometimes you have Pareto efficient Nash, sometimes you don't. In the case of a prisoner's dilemma, if you've heard about that, in the case of a prisoner's dilemma, if I were to set this up, this would be the Nash, and these 3 would all be Pareto efficient. So these things do not have to overlap. They're 2 separate concepts. They're 2 separate properties. All right, so that's our Stag Hunt game for our discrete example of a Nash. Any questions about that? So we just look at this payoff, and we can hopefully predict what the Nashes are by going through all the combinations. Okay, so More common case in engineering is the continuous game. And so for those of you interested in control theories, there's also this topic of differential games where you have a bunch of agents that move around in continuous space based on some differential equation and you sort of intersect game theory with dynamical systems and you get these differential games. In a continuous game, the strategy sets are continuous. And so every agent can choose from a subset of the reals. And so agents aren't choosing stag or hare, they're choosing any real number. And so you get the same payoff structure though. And so for every choice, you get a payoff to every agent that's based on the choices of other agents too. And the necessary condition for a Nash in a continuous game is this partial derivative. So the partial derivative of the utility for agent one relative to its decision variable when evaluated at the Nash is equal to the same for, basically they're all equal to 0 is what I'm going to get here. So for any agent or any actor, any player, then the partial derivative of their utility with respect to their decision variable, what they have control over, is equal to 0. If they all are mutually equal to 0, we have a necessary condition, not necessarily sufficient, but necessary condition for a Nash equilibrium. So this sets up inequations and unknowns. So if you have a dynamical system, like if you have a way that you know that your agents, your robots are changing their policy, you can put all of those together, set all of those policy changes equal to 0, or set their derivatives equal to 0, solve for that, and you solve for the Nash, and then you can say, do I like this Nash? This is something that if they come to equilibrium, this is the policy they're going to get. Do I like this? Is this sharing resources enough? When you're analyzing the so-called price of anarchy in multi-agent systems, you often want to say, well, if there's a perfect world and I had an orchestrator that could talk to all of my 100 agents, I would tell them all to do this, and it would give me a certain payoff. What is the global payoff when I'm at the Nash? And that's the so-called price of anarchy. And if that price of anarchy is too high for you, then you need to engineer something in your system that adds more coordination. Using that. All right, so that is the necessary condition for a Nash when you have these continuous games. This is a so-called variational inequality, or it's a special case of a VI. And so a variational inequality is just kind of a generalization of this idea where this statement here, I can generalize to consider boundary conditions, for example, like it might be impossible to actually get this derivative to be purely equal to 0 because I've got a constraint in my feasible space so that I can't actually get there. So I'm stuck in a wall in my decision space. And this will still work for those conditions here. So this is basically saying that the inner product, the dot product of your Nash, so imagine a vector that's coming from your Nash and it's radiating out to an alternative proposal. That vector, if I take the dot product of that and this so-called pseudo gradient, which is just basically these partial derivatives of the utility functions with respect to their local variable, if those two things are going in the opposite direction, then I'm at this equilibrium for this variational inequality. So the idea here is that if you're sitting at the Nash, if you consider any other point, if the direction from you to that point is positive, then the utility change will be negative. So that would mean that, if I don't want to move this direction because it's going to, likewise, if I'm going in my negative direction, if the utility change is positive, this sort of describes the bottom of a bowl. So in the bottom of the bowl, then the gradients here will all be equal to 0. But if you happen to be held away from that, so if I would like to roll downhill, but my feasible space stops here, so I can't continue to roll downhill, then this will tell me that that's okay if the only feasible direction is that direction, because I can't move that way, and that's uphill, then we're okay with you coming to equilibrium at a point that still has some slope to it, just so long as that slope is uphill in the direction you can move. That's all the variational inequality says here. So this is a more, and then, so emphasizing here that then this, if you collect all of these into a vector, that's what's down here. That's what this is, and that's the so-called pseudo-gradient. So it's not a real gradient because it's broken up among multiple utility functions. A real gradient would be partial u, not u1, with respect to each one of these. So you have partial u with respect to x1, partial u with respect to x2. That would be the members of the real gradient. The pseudo-gradient is you change what you're taking the partial of for every position. But it still is meant to describe the coupled motion of n selfish gradient colors. And so this idea here comes up in tuning, as I mentioned, generative adversarial networks, because in this case, if you're using stochastic gradient descent to train one neural network, and it is fighting with another neural network that's also being trained by stochastic gradient descent, then now you've got a system where one agent is following its utility function, its loss function, but it's affecting the utility, the loss of the other one, and vice versa. And so initially when they started using stochastic gradient descent, vanilla stochastic gradient descent, to find solutions to generative adversarial networks to solve for both the generator network. So this would be like a case where I want to find, I want to create something that hides information as much as possible in an image, like steganography. So I want to create something where I give it an image, it hides information by changing a few pixels on that image so that it can't be noticed by another. Well, then I generate another neural network that looks at the image and tries to extract the information. And I pit these two against each other. And whenever one neural network manages to find the information, it penalizes the other neural network. Whenever one neural network, whenever the original neural network prevents that, then it gets a benefit from that. So these two things, one of them is being trained to find the information, the other is being trained to hide the information. And when you put them with each other, then you end up getting kind of, they duke it out and they make for much stronger encryption. It has a better way, it learns to hide the information in that image in a better way. And so if you just use standard stochastic gradient descent, you get into these kind of saddle point problems where you get convergence issues. But it turns out that these variational inequalities, people like Dimitri Berzikas, people who do parallel numerical optimization, they've been studying variational inequalities for decades. They know all sorts of ways to solve these problems with parallel numerical methods. And those methods can be directly imported in the training of these generative adversarial networks. So that ends up being, you can, instead of training your network with vanilla gradient descent, two gradient descents, one running one network, one running in another, you instead use numerical methods that are specialized for this problem. You set them up in a formal game, and you literally try to force them into the Nash equilibrium because you know that that's where the gradients should go if they stabilize. So that's an example of the use of these in these computational. So that's what I mean there. It describes the outcome when you have multiple gradient climbers mixing. There are network optimization equilibria. So there's all of these network optimization problems and interdiction where you have people that you have two players, one player that is trying to break a network and another player that's trying to make the network move the most efficient. And these go to worst case analysis problems. So you're trying to imagine, like, if I'm trying to redesign an infrastructure system and I imagine all of the different things that could go wrong, I set up two processes, one that tries to create challenges and the other that tries to be robust to those challenges. And those network optimization problems that try to solve for the most robust network, those end up also looking like variational inequalities or Nash equilibria. And then, as I mentioned, there have long been a history of when you want to solve for very complex Nash, this becomes an ugly optimization problem, where people like Dimitri Berzikas, one of our sort of distinguished faculty here, has spent decades becoming a mathematical numerical expert in how to solve this using numerical methods that go beyond just using simple gradients. And so if you have a complex Nash that you want to solve for, then these numerical algorithms that are built to solve these variational inequalities will pop out Nashes. So me bringing up game theory and the Nash is not just a way to sort of start to introduce multi-objective, but I do think it's an example where kind of socially inspired modeling has directly interacted with engineering design, particularly in the case of multi-agent systems. And I think we'll potentially see more opportunities for this as we get more and more into agentic AI looking for. Yeah.
Are there any limits on what the Y can be? I do not understand why there would be why can't there be any Y which is which does not align with your G? Because are there any bounds on the Y?
Well, this is I should say for all Y that are feasible. So I kind of did a shorthand here. For all Y in feasible set. But that's the idea here, is that if we're at a candidate equilibrium, where can we perturb off of it in the feasible set? And then we draw a little difference vector from that point. And the variational inequality says, okay, now let's compare that to the pseudo gradient. And if they point in opposite directions, that's what this dot product means. So if the cosine of the angle between them is negative, then that is going to mean that you're at the Nash. So if it was positive, then what that would mean is that you should take this because you can now climb up the pseudo gradient. But this means that the only direction available to you, these are the directions available for you to climb. And these are the directions, like whether you're climbing or falling. And so what this is saying is that at the Nash, the only movement that's possible are downhill movements.
So essentially, if you are at the Nash, right, your G should always be 0, and that is why it never aligns.
That's if you're unconstrained. So if you're in a bowl, so the feasible set has the Nash at its interior, then that's the case. G should be 0. But in real problems, very often that continuous where things are flat is outside the feasible set. So the feasible set is supporting you so that you're stuck up, with some slope to it. So this is the unconstrained case up here, where they all equal 0. But in real cases, you might find that the point where these all equal to 0 is outside the feasible set. So the best you can do is you're rolling downhill and you would really like to go, you can see the bottom of the bowl right there, but then you hit a wall and you're stuck in that wall. And what this is saying is, well, as long as you're stuck at the wall, as long as gravity's pulling you into the wall, well, that's an equilibrium. That's a gravitational equilibrium. We're okay with that. You don't have to, it's okay that gravity's still pulling on you, even though the slope is not flat. Other questions? Not something we're going to drill down into a lot in this class, just something I want you to have familiarity with, or at least have seen before, is that I think games are important social drivers. If you've taken any AI courses, you probably at least had a brush with game theory. Games inspire us in thinking about multi-agent systems, inspire us about thinking about conflict. And the formalization here, variational inequalities, this is the way those of us in engineering who have really gotten deep into games, these are the numerical constructs we use to think about games. So I just want you to be familiar with that. I'm not going to ask you a lot about variational inequalities. Just know that a Nash can be expressed as a variational inequality, and just kind of marinate in this expression as being a generalization of that expression. Okay. All right, let's then I'll get into the meat of it. So that's if we have multiple agents that have conflicting agendas. That is a type of multi-objective problem. The different objectives are different agents that are not necessarily working for the same thing. Now, very often we have more cooperative versions of the same problem where we just have multiple things that we would like to be true, but the physics of the world prevents them from being true simultaneously. And that is the world of multi-objective optimization. So I'm going to open this with the standard example, the knapsack problem. So imagine that you have this problem. It's a two objective problem where I have n items I'm choosing from. Each item has a profit P, so if I manage to bring it with me, I make that amount of profit, and a weight W. And so I need to choose which items to include. So this is a binary decision variable problem. So for every one of these items, I'm assigning a 1 or a 0 to it. Do I take it? It's a 1. Do I leave it? It's a 0. So it's a set inclusion problem. So this is not a problem. It's a discrete problem. It's an integer problem. It's not a problem you can solve with a gradient climber or anything like that. We have two optimization objectives, two characters, two traits that we would like to optimize. We want to maximize total profit, but we want to minimize total weight. So the thing about that here, I can imagine that I've got all possible ways I could pack this knapsack. So that's what I've got on this x-axis here, and I call this is the number of items in my knapsack. And so for this number of items, there might be 3 different ways that I could pack that in there. So there's multiple options here. But so these are all the different ways I could pack my knapsack. And generally speaking, the more items I put in my knapsack, the more profit I make. For any particular set of items, there are going to be lower profit options and higher profit options, but generally speaking, that's the trend. So this suggests that I should just pack more and more into my knapsack. But I have this additional objective where I would like to minimize the weight of the knapsack. And so the idea here it looks very similar. I've got, as my knapsack gets more full, it gets heavier. But here, I want it to be as light as possible. So now I want the number of items to be as small as possible from this objective, but as large as possible from this objective. This is the standard multi-objective knapsack problem. Okay, so the idea here is we've got these two objectives in conflict. So if I were to give you this problem and say, hey, I want you to maximize profit, but I want you to minimize your fuel use, so you can't have an infinite trailer or something like that, or you can only bring with you what you can actually carry, then you have some benefit to say, well, I might want to minimize the weight and maximize it, because if I just maximize profit, that's fine, but if it's infeasible for me to actually get to where I'm selling these things, then that's not good either. Or it's just going to cost me so much physically or my fuel or whatever that it's not going to make up for what goes on here. So generally speaking, we're saying that these are at first incommensurable items. They can't be compared. They don't have a same currency. This is in dollars. This is in, I was going to say pounds, meaning, weight pounds. So one of them is a currency, the other one is a weight. All right, any questions about that problem? Okay, so this is a problem that often comes up in other classes, and a standard way to solve that. So there's a bunch of point-based ways to solve this problem. And so a standard way to solve that is to say we combine these two objectives together into one objective, one composite objective. And so I refer to this process as scalarization. I'm going to turn two objectives into a scalar option, to a scalar objective here. So I have some weight vector that is in 0 to 1 that weights the profit, and I subtract off 1 minus W of that of the actual weight. So unfortunately, I have capital W weight and lowercase w weight here. But so I can scale how much I care about profit and how much I care about weight by this W here. And so the question is, who decides the right scale there? So if I set it equal to 0, all I care about is profit. If I set it equal to 1, all I care about is weight. Well, neither of those are probably what I want. So do I set it somewhere in between? Who decides that? And so if I don't know what the right balance of that is, I might just be interested in knowing how do these two things trade off with each other. So one way you could do that is sweep through all of the different W options and just see what different knapsacks come out. And you might find that actually for a wide variety of Ws, you get the same knapsack out. in which case there really is no trade-off and I should just use that knapsack. Or you might find that there's a really sharp trade-off, and if I just add one more element, then my profit goes way up, even though my weight doesn't increase that much. So if I could sweep through all of these different balances, I might learn something. But so that's one way to do that. A similar way to do that is to ask for targets from your stakeholder. Your stakeholder might say to you, well, it's up to you what you put in your knapsack, but we really would prefer you make at least this amount of profit. Or, based on the vehicle that you're driving these things around in, you probably should be under this amount of weight. And so there's different ways you can come up with combining those things together with these targets. So that's what I'm kind of showing here, these target options. So in this option here, I say I'm minimizing the difference between my profit and a target and my weight and its target. So now I'm trying to actually regulate the profit to the profit target and the weight to the weight target, allowing for some slump. So if it's impossible to meet them both simultaneously, then this will find something in between. And I might need to add some little W and 1 minus W outside these to choose my balance between those, and then cycle through a bunch of different W's. So here I have the question of who decides this target, and do I need to rebalance these the same way I rebalance these? An alternative way you can set up targets is to say, well, I've just got a minimum profit and a maximum weight. I would like to be as much above the minimum profit as possible and as much below the target weight as possible. And I set up this objective that I try to maximize. So that's another way to do that. But again, is this the right balance? Do I need to put a W and a 1 minus W around here and tune those? Who decides these targets? And so on. Now, a bigger problem with both of these that is often not talked about in earlier classes where you might have seen the knapsack problem is that if you create these linear combinations, there are trade-offs that are missed. And we're going to show this graphically, is that if you simply sweep through all of the different balances, all of these different weights up here, there are going to be some combinations of knapsacks that you completely miss. And that has to do with whether they, basically imagine if this function and this function were both kind of sinusoids, and they might have different frequencies and kind of different phases. There are ways in which you can combine them together that, and I'll show this graphically to make this have more sense, that if you just maximize the combination here, there will be some trade-offs that are completely missed. They maximize this criteria, but they leave out other valuable trade-offs that just happen to not maximize this criteria, but are trade-offs, optimal trade-offs in some sense between these two criteria. So it turns out that we never use linear scalarization anymore because it has this blind spot. And we need to find a method that gets around this blind spot. Yep.
So kind of to reiterate or clarify, if you only care about finding like the global optima, linear combination, if you sweep it will find you whatever anything else will find you, but it might not find you something that's comparable, but like might have a preferable trade-off.
No, well, it turns out, so if we sweep this all the way through, so we kind of are looking for, I want to, global optima is kind of difficult to define in this case, but you can almost think of it as global optima for each W.
Yeah.
If I find a global optima for each W, and I sweep these W's through their whole range, 0 to 1, I will find a bunch of interesting combinations of profit and weight.
I guess my question is, is there a given W that like for some other method that doesn't have a tune, like hyperparameter that you have to tune, but it like does it automatically? Is it possible that you can find the same global optima as that one for that there's a W that finds that?
Yeah, so we are going to talk about methods that don't have W's, that find all of the combinations and more. They will find all of the ones that this will find and the ones that this will miss, and they don't have a weight. Now, I'll get into it here, but now there are newer weight-based methods that use a completely different metric called a Chebyshev scalarization, which is behind this tape here, that fix the problems that had up here. But we'll talk about that. So I'm just sort of laying out kind of a table of contents of where we're going here. All right, so most of you who've seen the knapsack problem before, how many of you have seen a knapsack problem in any class before? Okay, so you probably have seen this version where you set an upper bound on your weight or an upper bound on your volume of your knapsack. This is what's known as satisficing. So Herbert Simon is someone who's the sort of founder or one of the founders of this idea of bounded rationality, and it's this idea that we can't do both things simultaneously, so we're going to optimize one, and we're going to satisfy sufficient conditions for another. So this term satisficing, which is often held up as sort of in opposition to optimization, is the combination of satisfy and suffice, is where this funny word comes from. And so we can rewrite this optimization problem as maximize profit subject to a weight constraint. Now here, we can, who decides the weight budget? That's a subjective call. We can sweep all the weight budgets from 0 to infinity. And it turns out that will find every trade-off. So if I sweep this W from 0 to infinity, it is not guaranteed to find every optimal in the Pareto sense, and we'll get into what that means, that it's not possible to find every one of them with this here. But if by sweeping this max, this thing from 0 to infinity, I will find every way you can combine for every weight what is the best profit. This does not guarantee for every weight that you'll find what is the best profit. This one does guarantee that. So it does have the ability so the nice thing about this satisficing solution is if you really care about finding every possible trade-off to consider, then this provides you a way to do it. But it's not the most interpretable way. So it was really nice up here to have this W, which varied from 0 to 1, where we could say when W is equal to 0, we only care about profit. When W is equal to 1, we only care about weight. But it's hard to sort of say when this upper target for weight, when it's equal to 0, clearly we only care about profit. Or no, clearly we only care about weight. But when it's set equal to infinity, clearly we only care about profit. But when it's set equal to 100 pounds, it's not clear whether we're more profit-seeking or weight-seeking at that point. So it's less interpretable because you have this, again, incommensurable currencies here. The profit and weight don't share the same currency. So a more modern way to do scalarization is what's called Chebyshev scalarization or weighted minimax. So this sort of is the solution that if you really have to solve this by sweeping through weights, like we want to do here, you really should do it with this method down here. So in this method, it's uglier to look at for sure, but the idea here is that we consider, for one, we have to solve for the single objective optimizer. So this is the knapsack that maximizes profit. This is the knapsack that optimizes weight. So in the case of the knapsack problem, this would be an empty knapsack, and then who knows what this would be over here, this profit one. But once I know that single objective one, then I can look at how far away is my weight from the optimal weight, and how far away is my profit from the optimal profit. And I can take that difference, and then I can scale it by some scalar, some W and 1 minus W. And then based on those weightings there, I can take the maximum weighted difference. And the goal of Chebyshev scalarization is to minimize the maximum weighted difference. So of all possible knapsacks, I see how different they are from their single objective optima. And then from there, I try to find the knapsack that's sort of the nicest balance, as closest as possible with these weight preferences, these W preferences here, so that I kind of bring those in line there. And if I do that for every possible W from 0 to 1, then it guarantees, like the satisficing case, that I will find every possible trade-off between profit and weight, or my two objectives. So these are the four different ways we can scalarize. And it turns out that two-objective, multi-objective optimization with genetic algorithms doesn't use any of them. There is another way to do things that I think is actually more intuitive and more satisfying, not sufficing. But three-objective optimization and higher uses this down here. So this is a little bit outside of the scope of the class. I'm really going to focus more on the two-objective. And the story here will be like, this is before this class. I'm guessing you've seen some of these before. And this would be the kind of standard way to use single objective thinking to solve multi-objective problems would be here. But the modern way to solve two objective problems is not to use any of these. And we're going to talk about that. But the modern way to solve three objective problems higher is to use this one in a special way, which we'll get into, which I won't get into, I'll hint at. And then if you study MOEA/D, which is this decomposition evolutionary algorithm, that is something that's an opportunity for your final project. If you're interested in looking into it, it leverages evolutionary algorithms with this Chebyshev scalarization to solve it for three and higher. But I'm getting kind of ahead of myself. All right, any question about these of like this general idea that there are ways to scalarize multi-objective problems, to take multiple objectives, turn them into one objective, and then either just solve the one objective for one balance or sweep through all possible balances and then hope that tells you about every possible mixture of solutions. Is that clear to the general idea? Yep.
How is that one trade-off at a time?
Like, how is this one trade-off at a time?
Even the ones below, because at that point of time, you're only looking at one of them, right? So it's not a trade-off, right?
Well, it is a trade-off here, but like, so this uses, there's a smoothness issue. So like, if I were to talk about up here, I think it's pretty clear that if I set W to 0.5 or whatever, it's a mixture. But I think when you get down to here, it seems weird because you kind of switch from one to the other. Is that kind of what you're saying here? And that is a very important point. So up here, this is about, so without getting too much into the mathematical weeds, but we talk about different norms. You know, if you ever take a good linear algebra course, you talk about all these norm spaces and whatever, and two norms and three norms or whatever. This thing leverages what's called the infinity norm or the maximum. And so if you take, like, if you know that like as the crow flies, we call that the two norm. So the distance, the triangle formula, the distance between me and a point over there, straight line distance, that formula there is called a two norm. The one norm will be adding up like the Manhattan distance. Like I can't actually walk from here to there. I have to walk down the road and over. If I walk the amount of distance I have to walk along the roads and add those together, that's called the one norm. So as you get, there are all these different ways to sum up the difference between one point and another. And as you go from one norm to two norm, whatever, what you're doing is you're changing the weighting of the different components. So in the one norm, I weight the amount I have to walk this direction, and the amount I have to walk this direction equally, and I add them together. In the two norm, it starts becoming more important which one's larger. It's a little bit more triangular. So if I'm walking diagonally across here, then if one direction is much larger than the other direction, it will dominate that triangular distance. As you go higher and higher in these other norms, then you gradually start making the one that's longer more important, but you're always including a little contribution from the one that's shorter. At the limit, the so-called infinity norm, this is what you get, where the distance between you and the point is the maximum component. And it turns out that the thing that rescues this from the non-convexity problem that happens up here, which we'll demonstrate graphically, and all this will stop sounding so abstract. The problem here is that this thing, it has this smoothness characteristic, which finally, at the singularity in norms, when you go to the infinity norm, is dropped. And that is what allows us to explore the entire space. So exactly the weirdness that you're talking about, where it seems like it's not a trade-off because you're sort of switching from one to the other, is a singularity that is induced that actually allows us to find things that this smooth case can't find. But that's getting really abstract. I could spend, you know, if this is a good linear algebra course, I could spend 2 weeks talking about all of that and, you know, how we get from here to there and what does it look like in terms of level sets and all of that. That's outside the scope of this course. But the people who developed all of this is what was in their heads when they were developing. All right, so scalarization, that's in this slide, that's what you take away here. Scalarizing, that's one method. That's not the method we want. So let's then go back to the drawing board, so to speak, and think about other ways to talk about multi-objective problems. So that aren't so scalarized. So let's imagine that I have two objectives. So I have this objective up here, and I've got this second objective that I'm just plotting in the negative, but it's positive. So positive F2 is going down, positive F1 is going up, and it's my goal to maximize both. So if I could find a solution that was simultaneously max in F1 and max in F2, then that would be the best solution. That would be the solution that I should suggest to the stakeholder. The stakeholder comes to me and they say, I care about speed and I care about accuracy. And this is speed and this is accuracy. If I were to find a design that maximized speed and maximize accuracy, I would be an idiot not to sell that at a high price to my stakeholder. But most likely, I can't get maximal speed and maximal accuracy simultaneously. I have to choose a mixture. So if this is my speed curve and this is my accuracy curve, and these are all of the designs that I can give my stakeholder, then I have to ask myself, what designs are even eligible for me to consider giving my stakeholder? So, does anyone think this is an eligible design to give my stakeholder? Why not?
Because the total distance, if this distance is not the maximum, so we find to make this vertical line to be as maximum as possible.
So you say should I move to the right or the left? I should move to the right. So moving to the right improves both objectives simultaneously. Over here, moving to the left improves both objectives simultaneously. That's what's known as a Pareto improvement or Pareto movement. So I could write that in here if that's helpful. I can say here, this is a Pareto improvement, just as this is a Pareto improvement. So in both sides here, so that sort of suggests that if I highlight here, maybe I'll highlight in red, here and here, I would argue I am a crap designer, a crap engineer, if I recommend my stakeholder take any design in that highlighted space. Why? What's wrong with the highlighted area of engineering designs? Yeah.
Because so we want to get the maximum feature of both the traits. So we like the left of the max of F2 and the right of the max of F1. Those spaces gives the minimum area, but whatever the maximum or our final optimized solution we want, it would be between the max of F2 and between the max of F1.
Maybe I'll use a different color just for red green. Right, so what we're saying here is I should select things in between here. Can I use the wording of Pareto improvements? Are there any Pareto improvements in the blue area? There are improvements in the blue area? If I was in the blue area, there's no way I can move in the blue area to make a Pareto improvement. If I move this direction, I improve in one objective, but I go the wrong direction in the other objective. The blue area is the trade-off area. And that is the so-called Pareto-efficient set, or it is Pareto-efficient, Pareto-optimal. So it's a position X where it is impossible to make any Pareto improvements. And so we would say that we often refer to when we make a Pareto improvement, the place that we move to dominates the other one. So here I say that X dominates dot. So dot moved to X, X dominates dot. But anything in the blue dominates anything, well, not necessarily anything in the red, but there are points in the blue that dominate points in the red. There are no points anywhere that dominates points in the blue. So this blue set we sometimes call our non-dominated set, which is Pareto efficient. It's efficient because we squeezed out all of the Pareto improvements. So it'd be inefficient if there are Pareto improvements left. This came from social welfare theory originally, and it was the idea that if a policymaker could manage to make a change in policy in government that would make everyone in the society better, they should do that. That, if it makes everyone better, including them and everyone else, that is a Pareto improvement. And so we want to live, supposedly, in a society where policymakers put us on the Pareto efficient set, because that's where we start having useful discussions. If the discussion is, should we step into an area that's better for everybody? There's no discussion to be had, we just should. If there is a movement that can be made that makes it better for everybody, we should do that. But here, and this is where you have interesting subjective decisions. So this is where you start getting subjective. So here, things are objectively bad here. Objectively bad in this region, and likewise objectively bad in this region. But they are subjectively, open for discussion in this region. So that is the so-called Pareto efficient set or non-dominated set. Okay, so that's one way we can visualize this. Any questions about this? So we want an optimization algorithm. So the scalarization methods, that old school way of thinking, that puts subjectivity first. That says we're going to decide on the weighting ahead of time and then solve for the best given the weighting. This puts subjectivity second. This says we're going to find all of the points there where we're willing to have a discussion and then decide on the weighting. And we, the engineer, are not deciding on the weighting. We are going to hand the stakeholder this tiny little set and say, these are the only things you should be discussing. Because everything else you can do better. And then they can say, oh, well, that's interesting. Now that you've shown us that set, then we notice that this one happens to be better in some other criteria that we forgot that we had. And so we're going to now select this one. So there often are hidden criteria when we talk to stakeholders, and giving them sets of options helps engage with those hidden criteria. All right, but when we summarize these things, we don't often use this decision space. We use the so-called criteria space. So rather than plotting the decision variable, we do a parametric plot. So if you'd like, I can say this is F2 of X and this is F1 of X. And so every point is a particular X expressed in both F2 and F1 simultaneously on the same space. And this is what we call the objective space or the criteria space. Or if we want to get to the biology, the character space or the trait space. In this space, all of these points down here are potential ways that we can combine weight and profit, or two different objectives. Now, if we can do this, if we can move this particular way, that is a Pareto improvement. Because that is an improvement that is going to improve one objective without hurting the other. So this is a Pareto improvement, this is a Pareto improvement, this is a Pareto improvement. All of those are Pareto improvements. And this line right here, this is where that stops. From this point here, where you've got the maximizer of F2 on one side, the maximizer of F1 on the other side, it's impossible to make Pareto improvements anymore. You've run out of room. And this green line down here, that is our so-called Pareto frontier. So the Pareto-efficient set are the set of decision variables in this trade-off space. The trade-off space in objectives, like how the two objectives trade off from each other, that's the Pareto front or Pareto frontier. The set of all Pareto optimal solutions in the objective space. This is our fundamental trade-off surface. And the challenge will be, as we'll show graphically here next time probably, is that this can be non-convex. And those linear ways to find this Pareto frontier, it turns out they don't find the non-convex parts. So they end up shading out these parts. So they only find the stuff up here, they only find the stuff out here, they don't find this. And I'll show you why, again, in a graphical approach in a couple of slides that we'll probably do next time. Questions about this? Pareto frontier, Pareto front, that's just this line here. Pareto-efficient set. Okay, so I work on a lot of optimization problems where our stakeholder has no idea what this looks like. And so we need to then provide to them a sample of this so that they can say, oh, I had no idea. Like, it might be that just the physics of the problem, that this thing is straight up and down, it's straight horizontal, it might be a single point. They have no idea what it looks like. And giving them that now helps them decide. They can come out, they can finally figure out what the marginal rate of substitution is between these two quantities. How much do you give up of one quantity to gain another quantity? If they know that, then they can say, actually, it's pretty cheap for us to give up a lot of this, or to gain a lot of this in terms of this quantity. If we give up just a little bit of this one, we gain a lot of this one. And they only will know that if they know the shape of this frontier. So, like bringing all that together, and then I'll stop here. So the solution here is a set-based concept. It's a set of objectively reasonable choices, no subjectivity. Optimization should start conversations, not end them. The old school way of thinking of optimization is I give you a point, you shut up, you take that point, and you go and implement your system. The new way of thinking of optimization, more productive way of thinking of optimization, is optimization gets rid of the bad choices and only leaves you with good choices. And then you can start the conversation with that. So population-based evolutionary algorithms are going to be really good at this because all of that diversity, that community, at GA, it was a waste. Like, you used it to search the space, but then gradually, especially with CMAES, it then collapses to a point and it says, here's your optimizer. I've got 100 individuals clustered at one point. Well, can't we use those 100 individuals? Wouldn't it be great if all of them converged, like they help each other, but then over time they separate and they somehow spread out, and then suddenly the population becomes the output. And that is what we can do with population-based evolutionary algorithms. The key challenge here will be trying to get that population to move toward that front. What is the right fitness concept that drives a population toward a set attractor, not a point attractor? How do we define fitness? And then on top of that, how do we try to get spread out along that set so we're not finding one point on the Pareto frontier, but the whole Pareto frontier? These are the challenges that we're going to solve as we look towards these multi-objective evolutionary algorithms. All right, I don't want to keep any longer. If you have any questions, feel free to come up. Otherwise, we'll see you on Thursday. We'll pick up with this a little bit.